Hello everyone. Today we're going to explore two of the most fundamental concepts behind every LLM, tokens and embeddings. These are the building blocks, the very foundation of how models like ChatGPT and Claude process and understand language. Here is the thing, neural networks don't actually understand words or language the way we do. They understand numbers. So there is a crucial transition layer that converts human language into numbers the model can work with and then back into language we can read. The translation layer is built on tokens and embeddings. In this session, we'll unpack what tokens are and why we use them, how tokenization actually works, including algorithms like byte pair encoding, what embeddings are and how they capture meaning, the famous idea of meaning as geometry in vector space, positional embeddings and why word order matters, how all of this fits together in a real LLM, practical implications for cost, context windows, and multiple languages. By the end, you'll have a solid understanding of how language becomes numbers and how these numbers capture meaning. So let's dive in. Why machine need tokens? Let's understand this. Why do we even need tokens? Why can't a model just read text the way we do? Computers and neural networks operates on numbers. Every input to a neural network must ultimately be numerical. Text to letters, words, punctuation is not inherently numerical. So we need a systematic way to convert text into numbers. That conversion starts with breaking text into units called tokens. The obvious idea would be treat each word as a unit and give it a number. But this has serious problems. There are millions of words across all languages, plus names, technical terms, slang, and constant new coinages. The vocabulary that large is impractical. No matter how big your word list, you'll encounter words you have never seen, new terms, new typos, rare names. A pure word based system breaks on these. But a word based system treats them as completely unrelated tokens. That's wasteful and loses useful structure. The opposite extreme is to use individual characters as tokens. This solves the vocabulary problem. There are only so many characters, but it creates a new issue. Sequences become extremely long. A single sentence becomes hundreds of characters, and the model has to work much harder to learn that sequences of characters from meaningful words. It's inefficient and makes learning harder. The solution most modern LLMs use is subword tokenization, a middle ground. Common words become single tokens, while rare or complex words are broken into meaningful subpieces. For example, the cat, run, common words, they are single tokens. Tokenization might split into token and ization. Unhappiness might split into UN, HAPPI, NESS. This gives us the best of both worlds, a manageable vocabulary size, the ability to represent any word by combining subword pieces, shared pieces across related words capturing structure, reasonable sequence lengths. This is the sweet spot and why subword tokenization dominates modern LLMs. Now, let's get concentrate about how tokenization actually works. How does a system decide where to split text and what the token should be? Every LLM has a component called a tokenizer. It has two jobs, encoding and decoding. What's encoding? Converting text into a sequence of token IDs. And what is decoding? Converting token IDs back into text. The tokenizer has a fixed vocabulary, a predefined list of all possible tokens, each with a unique ID number. When you input text, the tokenizer scans the text, breaks into it breaks it into tokens from its vocabulary. Each token is mapped to its ID number. The sequence of IDs is what actually goes into the model. For example, the sentence I like AI might become I like AI, which map to IDs like some numbers 40, 18. 95. Notice that spaces are often included as part of tokens. That leading space before like and AI is significant. Byte pair encoding. What is byte pair encoding, BPE? The most common algorithm for building the vocabulary is byte pair encoding. Let's understand how it works because it is elegant. BPE builds its vocabulary from training data through a merging process. Start with a base vocabulary of individual characters. Scan the training text and find the most frequently occurring pair of adjacent tokens. Merge that pair into a single new token and add it to the vocabulary. Repeat, finding and merging the next most common pair thousands of times. Stop when you reach the desired vocabulary size. So, over many merges, frequently occurring sequences, common words and word parts become single tokens, while rare combinations remain split into pieces. The result naturally reflects the statistics of language. Common things get short representations. A simple example is imagine training text with lots of low, LOV, LOW, LOW or lower, and lowest. Start with the character L, LOWERST. I and O often appear together. L and O often appear together, merge into LO. LO and W often appear together, merge into LOW. Now, low is a single token and lower becomes LOW plus ER. You can see how algorithm discovers meaningful subword until the units automatically just from the frequency. There are related algorithms you might hear about. Word piece used by BERT, similar to BPE, but merges based on a slightly different criteria. Unigram starts with a large vocabulary and prunes it down. Sentence piece, a toolkit that treats text as raw bytes, handling any language without needing spaces. Great for languages that don't use spaces between words. The key takeaway here is tokenizers learn their vocabulary from data, discovering the most efficient way to break language into reusable pieces. Now, to try to put tokenization into practice, they affect real things like cost, performance, and working with different languages. When you use commercial LLM APIs, you typically build per token, both input and output. Understanding tokens directly relates to understanding your costs. One token is 4 characters, one token is 3/4 of a word. So 100 tokens is 75 words. So a 1000 word document is roughly 1300 tokens. Knowing this helps you estimate and manage costs. Tokens and context windows. LLMs have a context window, the maximum number of tokens they can process at once, including both your input and the model output. When you hear a model has 128K context window, that means 128K tokens. Everything you your prompt, the conversation history, and the response must fit within that token budget. This is why very long documents sometimes need to split or summarized. Here is something important. Tokenization efficiency varies dramatically across languages. Most tokenizers are trained predominantly on English, so English text tokenizes efficiently, few tokens per word. Other languages, if you take, especially those with different scripts, often require more tokens for the same meaning. This means non English text can cost more and consume context faster. This is an active fairness and efficiency concern in the field, and newer tokenizers work to be more balanced across languages. So, tokenization affects behavior. Interestingly, tokenization can affect model behavior. For instance, models sometimes struggle with tasks like spelling or counting letters in a word, partly because they see tokens, not individual characters. A word like strawberry is a few tokens, not a sequence of letters. So, counting the letter R is not as natural for the model as you would think. Understanding this explains some quirky model behaviors. Now, let's go to tokens and embeddings. So far, we have turned text into token IDs, that is numbers, but there is a problem with these IDs. And solving it brings us to embeddings, the second half of our story. Token IDs are just arbitrary labels. Token 5000 is not more than token 100. The number 1842 for love has no meaningful relationship to the number for like or hate. The IDs carry no information about meaning. They are just index numbers into a vocabulary. If we fed these raw IDs into the model, it would have no starting sense of which words are related. We need a representation that captures meaning. That's what embeddings provide. An embedding is a vector, a list of numbers that presents a token in a way that captures its meaning. Instead of like being the single number, it becomes a vector of maybe hundreds of thousands of numbers. The dimensionality, the length of this vector is a design choice. Common sizes range from a few hundred to several thousand dimensions. Larger embeddings can capture more nonce but cost more compute. The model has an embedding layer, essentially a big lookup table. It's a matrix with one row for every token in the vocabulary, and each row is that token's embedding vector. When a token ID comes in, the model simply looks up the corresponding row to get its embedding vector. So the flow is text to tokens, tokens to token IDs to embedding vectors. These embedding vectors are what actually flow into the transformer layers. Crucially, these embedding vectors are not hand designed. They are learned during training. Initially, they are random, but as the model trains on massive amounts of text, it adjusts these vectors so that they capture meaning. How? Because the model's task predicting the next token works better than when related words have related embeddings. Through training, the result is that embeddings capture semantic relationships. Words with similar meanings end up close together in this high dimensional space. Words with different meanings end up far apart. This is what lets the model understand that a sentence about a dog is related to one about a puppy, even though the tokens differ. This idea that meaning can be represented as position in a vector space is one of the most profound and powerful concepts in modern AI. So let's understand the meaning as geometry. That's the vector space. Imagine a space, not the 2D or 3D space we are used to do, but a high dimensional space with hundreds or thousands of dimensions. Every token's embedding places it as a specific point in space. The entire vocabulary becomes a cloud of points. We can't visualize hundreds of dimensions, but we can reason about it. The key properties: distance represents similarity. Points close together have similar meanings. Direction represents relationships. Movements in certain directions correspond to meaningful transformations. Words that appear in similar contexts end up near to each other, like cat, dog, hamster, rabbits. These are all pets. They cluster together. Happy, joyful, delighted, cheerful. This is clustered together. Run, sprint, jog, dash. This is clustered together. To measure similarity, we often use cosine similarity, essentially measuring the angle between two vectors. Vectors pointing in similar directions are similar in meaning. This is how systems find related concepts, power semantic search, and more. Here is a classic example that stunned researchers. In a well trained embedding space, relationships are captured as consistent directions. The vector arithmetic: king, man, woman equal to queen. Think about what this means. If you take this vector for king, subtract the vector from man, and add the vector for woman, you land very close to queen. The embedding has learned the concept of royalty and the concept of gender as directions in space purely from reading text. Let's take another example. Paris minus France plus Italy equal to Rome. This is the capital of relationships. Walking minus walk plus swim equal to swimming. It's just a verb tense relationship. These are not programmed, they emerge from training. The geometry of the space encodes real semantic and grammatical relationships. Now, an important evolution. Early embeddings like word to vec and glov gave each word one fixed embedding, but words have multiple meanings. Bank means something different in riverbank versus money bank. Modern LLMs use contextual embeddings. As the token flows through the transformer's attention layers, its representation is updated based on surrounding words. So, bank in riverbank gets a different final representation than bank in savings bank. The initial embedding is just the starting point. Context refines it. This was a major leap in capability. This geometrical representation of meaning is what enables semantic search. Finding by meaning, not keywords. Okay. So recommendation systems, clustering relation concepts, and fundamentally the more model's ability to reason about language. Embeddings are how machines represent meaning, and it's a genuinely elegant solution. Now, let's go to positional embeddings. There is one more crucial piece of the puzzle: positional embeddings. To understand why we need them, we have to revisit how transformers work. Unlike older models that read text word by word in order, the transformer's attention mechanism looks at all the tokens simultaneously in parallel. This is great for efficiency, but it creates a problem. The model has no inherent sense of order. Consider these sentences: the dog chased the cat chased the dog. Same words, completely different meaning. Determined entirely by order, but if the model sees all tokens at once with no position information, these would look identical. So we need to inject information about where each token sits in the sequence. So the solution is positional embeddings. Positional embeddings add information about each token's position to its embedding. Before the tokens enter the transformer layers, we combine the token embedding, exactly the word means, and the position embedding, where the word is. Now, each token's representation carries both meaning and position. The model can distinguish the first, the from the second, and understand word order. There are several approaches like sinusoidal position coding, learned position embeddings, rotary position embeddings, relative position methods. So, positional embeddings are essential. Without them, LLMs could not understand grammar, word order, or the sequential structure of language. They are the piece that lets a parallel processing model still respect the sequential nature of text, and advances in positional encoding like ROP are directly tied to models handling longer and longer context windows. So, if we try to put it all together, how tokens and embeddings work to the real LLM from your text input to the model's output. Here is the full journey. Step 1 is tokenization. Your input text is broken into tokens by the tokenizer using its learned vocabulary. Hello world becomes tokens, each mapped to an ID number. Step 2, token embedding lookup. Each token ID is used to look up its embedding vector in the embedding matrix. Now each token is a rich vector capturing its meaning. Step 3, add positional information. Positional embeddings are combined with the token embeddings. So each vector now encodes both meaning and position. Step 4, transformer layers. These combined embeddings flow through the stack of transformer layers. At each layer, the attention mechanism lets tokens exchange information, and the representations are refined. This is where contextual understanding happens. Each token's representation is updated based on all the others. All the others. Step 5, output embeddings to probabilities. After the final layer, each position has a rich contextual vector. For text generation, the model takes the vector at the last position and converts it through a final layer into probabilities over the entire vocabulary. This tells the model how likely each possible token is to come next. Step 6, selecting and decoding. The model selects the next token based on these probabilities. The token IDs is then decoded back into text, and for generating more, the new token is appended and the whole process repeats. Embeddings beyond LLMs. It's worth noting that embeddings are useful far beyond text generation. Embedding models are used specifically to convert text into vectors. It's used in semantic search, finding documents by meaning, used in retrieval, augmented generation RAG, giving LLMs relevant context, clustering and classification, recommendation systems, detecting similar or duplicate content. In these applications, we often create a single embedding for an entire sentence or document, capturing its overall meaning in one vector. This has become a huge field of its own, powering modern search and retrieval systems. So, we covered a lot of ground. Let's consolidate everything into key takeaways. Neural networks need numbers, so text must be converted starting with tokens. Tokens are subword units. Byte pair encoding and similar algorithms learn a vocabulary from data by merging frequent pairs. Tokenization has real practical impact, cost, context windows, and language fairness. Quirks of tokenization explain some odd model behaviors like difficulty spelling. Token IDs are meaningless labels. Embeddings give token meaning. Embeddings are learned vectors that capture semantic relationships. Meanings become geometry. Modern LLMs use contextual embeddings, defined by attention based on surrounding words. Transformers process all tokens at once, losing order information. Positional embeddings inject position. Techniques like sinusoidal encoding and ROP encode position enable longer contexts. So, understanding these tokens and embeddings demystifies a huge part of how LLMs work. When a grasped language is converted into points in a high dimensional space where meaning is captured by geometry, the magic of these models start to make sense. It's elegant mathematics and clever engineering. The journey from raw text to machine understanding begins with these two ideas: breaking language into tokens and giving these tokens meaning through embeddings. From this foundation, everything else in the language model is built. It's a remarkable example of how the right representation can transform an impossible problem, making machines understand language into a tractable one. So, finally, thank you so much for watching this deep dive into tokens and embeddings. If it helped you to understand how LLMs process language, please give a thumbs up. Subscribe for more AI content. So until next time, keep learning and stay curious. Thank you.